Hello everyone. In the previous session, I have explained the concepts of basics regarding composition of relation. Now, in this module, let me continue the same concept with reference to matrix of relation. In the sense, composition of relation in terms of matrices. How can we decide? Suppose matrix of relation. For any relation R, you are familiar to write matrix of a relation. So while marking a matrix of relation, how you are going to write? Suppose if in a relation R, if there exists an ordered pair AB, then you are going to mark it as 1. In the sense, suppose in general, I am going to write it in general form. If AI matrix of relation is equal to 1 when AI comma Bj belongs to R, right? And matrix of relation is 0 when AI comma Bj does not belongs to R. Am I correct? Now similarly, suppose if I have another relation, say yes, I am going to write a matrix of relation for that particular relation yes. Here also I am doing the same procedure. Matrix of relation S is equal to 1 when, say, an element Bj, Ck I'll take belongs to R. In the sense, I am continuing the same element. Why? Because I have told you in the previous class, suppose if in a relation R I have an element like 1, 2, in a relation I have to search for an element which starts with 2. Right? Then in matrix of relation, composition relation ROS, I am going to write 1, 3. Suppose in a relation R, I have an element 1, 2. In relation S, I have to look for an element which start with 2. So if I have 2, 3, then in matrix of relation of its composition, we are going to write 1, 3. That is what we are doing. So I am applying the generalized concept now. In a matrix of relation, I have chosen the element AI Bj. Same element has to be continue in the second relation. This is what the thing is. See here, in the previous module, I have explained this same example. You just go through that. In a relation R, suppose if I have an element, look at here. Suppose if I have an element 1, 2, I am going to look for the second relation yes, in which 2 start with. So I have 2, 4. So I am going to write 1, 4 in a relation of its composition, that is ROS. So the same thing I am doing for matrix of relation. I have chosen an element AI Bj, so I am going to pick a same form, that is Bj Ck in a given relation. Fine. Then again it is 0 when Bj, Ck does not belongs to R. Now if you are writing its composition, R composition yes, then I can write it as 1 only when these conditions satisfied. In the sense, in its composition matrix, an element will be 1 only when these two elements are present. I can write AICK. This element is present. This element is present, then only composition is 1, right? Why? Because if this element present, then AI Bj should be in R and Bj Ck should be in yes. This is very important concept in order to understand the next theorem. Make sure I am repeating once again. If in a matrix of relation AI Bj is there, then in matrix of second relation the same continue element Bj Ck should be there. Then we can talk about its composition is 1 only when these two elements belongs to the relation, then only this element belongs to relation. The meaning is that if this element is there in the particular matrix, then only we can mark it as 1. If that was the case, we can mark the same for its composition as well. And similarly, it is 0 when AICK does not belongs to R. So, in short, I can write if an element AI, say I'll write one with reference to one single element so that you can understand clearly. If AIK is an element in matrix of relation, take an example. Instead of taking ordered pair, I'll take it in generalized form. Suppose in MR, I have an element AIK. Fine. Then if in MS, I have an element, say B, K, J. Continuous there. Look at the suffixes. K is in matrix of relation R, it is ending with suffix K. So in matrix of relation S, it is beginning with K. Right? Suppose in its composition, I have an element, say D. C or else C also you can take. So I'll take C only. Fine. So if I'm going to take C, I have to write IJ. Fine. See here, I am going to eliminate this common term. I am going to write IJ. It is similar that, see here, in R I have an element AB. In S I have an element BC. Then in its composition I am going to write AC. Right? In the same way, in matrix of relation R, you must and should remember this. In matrix of relation R, if I have A, I, K, in matrix of relation S, if I have an element B, K, J, since it is common, right? Then in its composition, you should have ending element C, I, J. That is ending suffix you should have. Meaning is, if AIK is equal to 1 and BKJ is equal to 1, then CIJ will be 1. Or else I can say CIJ is 1 only when these two element is 1. Cij is 1 only when these two element is 1. Similarly, Cij is 0 only when these two element is 0. Hope it is clear for you. Now, let me discuss one theorem based on this concept. Here is a theorem statement. It is important theorem. Now look at the statement. Let A, B, C are three finite sets. Three finite sets is given to us. Generally composition is none other than I have a first relation, say I'll tell you the basic like G. I have a relation G from A to B. And I have a relation F from B to C. Then the composition G of F will be relation from A to C. This is what the general meaning of composition is. Now look at this theorem. I have a relation R from A to B. Next I have a relation S from B to C. Now we have to prove M composition RS will be equal to matrix of relation into matrix of S. The meaning is that when you are going to write composition matrix, that should be equal to matrix of relation multiplied with matrix of relation S. Anyhow, this will be true for all the problems. While doing problem, I will verify the same. But how can we convince through the proof? Let me do that. Suppose let me take a set A, set in the sense I have defined a relation. Obviously, it is a non-empty set. I have given, moreover, all these three sets is given in the problem itself. Let me take an element of set A is A1 to AM. Similarly, set B as B1 to Bn. And set C as C1 to Cp. Now, let us define matrix of relation for R. Why? Because I have three relations here. Matrix of relation, I'll discuss in terms of first an element. Suppose it contains an elements of form Aij, and matrix of relation S will be of the form B. Just now I have explained, no? I'll take that only, though, so that you will understand very well. Aik, MS will be BKJ. Similarly, MR composition S will be CIJ. MR composition S will be C. This is common, so left with CIJ. Fine. Now, from the concept of ordered pair, I can write like AI, B, J. Suppose if AI, BJ belongs to a relation R, then in MS, BJ, CK should be in R. Then only I can talk about AI, CK. Just now I have explained the same thing. I have to write it in a statement form. That's all. Then this should be belongs to R. Then only this element exists. Right? So if all the elements, if these two values is equal to 1, then only this element value is 1. Otherwise, it is 0. And hence I can say MR dot MS, either in matrix of relation. This is what MR is, either in matrix of relation or in matrix of relation. Yes, when you're going to multiply, when AI BJ belongs to R, you will get 1 here. When BJ CK belongs to R, you will get 1. So if you're going to multiply, you will get the value as 1, right? In MROS also, in the sense composition also, if this element belongs to R, you will get 1. Suppose, I'll tell you in depth. Suppose in the first case, let me take, if both the elements are present in R and S. If it belongs to R, in the sense ordered pair, general ordered pair, I'll tell you. If in R and S, elements, let's say, if in a relation R and S, an ordered pair belongs to R in the sense, you will take it as 1. If it doesn't belongs, you will take it as 0. In the composition also, matrix of relation R, matrix of relation S. In the composition also, if an ordered pair belongs to R, then you're going to take it as 1. If it doesn't belongs to R, then you're going to take it as 0. So when you're going to multiply 1 of relation R and S of relation R, you will get 1 only. Again, in relation R is 0, then in relation S, whatever may be the value, 0 into anything will be 0. So I can write matrix of relation composition S is equal to matrix of relation into matrix of relation S. I'll repeat once again. The key point is that when an ordered pair AI BJ belongs to R, then only matrix of relation value will be 1. If it does not belongs to R, the matrix of relation value is 0. Similarly, in the matrix of relation S, if this ordered pair belongs, the value will be 1. Otherwise, it is 0. So, when you're going to multiply matrix of relation with matrix of S, 1 into 1 will be 1. Again, 0 into 0 will be 1. Again, in its composition, it takes either 1 or 0. So, I can say MROS is equal to MR dot MS. You can prove this by using the counter example as well. Fine. Now, you have a next theorem. And here is a statement. Before going to prove this theorem, remember M or else I can say R composition S will never be equal to S composition R. As I told you, ordered pair 1, 2 will not be equal to 2, 1. Why? Because when you're going to draw the same in a graph, suppose 1, 2 will be when x is 1, the value of I is 2. 2, 1 will be here. So clearly these 2 points are different. So ordered pair will never be equal, in the sense A, B will never be equal to B, A. So R composition S will never be equal to S composition R. Now coming to the second theorem, if R is a relation and a set A, then R is transitive if and only if R square is contained in R. Meaning is R square is contained in R. Contained in the sense subset of R. Now let me prove. First let me take R is transitive. R is transitive. So I have taken R as transitive. I have to prove that R square is subset of R. Right? Now, as when I am doing the composition of relation, I have told you how can I write R square as R composition R. R composition R will be the value of R square. Right? So, in the previous session, while doing the composition of a relation, I have told you regarding this. That is, suppose if I have an element, say x, y belongs to R and y, z belongs to R, then x, z is also in R square, or I can say R composition R. Right? I'll give you one more example. See here, suppose if I have an element, say, or else relation, say R, with an element 1, 1, 1, 2, 2, 3, 3, 4. Now, let me find its R square, in the sense R composition R value. So, 1. Again, in order to avoid the confusion, let me write the set R once again. 1, 2, 2, 3, 3, 4. Now, composition. When I am going to take 1, 1, I have to look at the element which start with 1. The possibility is either I have to take 1, 1 in here or I have to take 1, 2 here. Fine. So the continuation of element is there. So I have to write 1 1 and 1 2. Next, suppose if I am going to take 1 2, I have to look at an element which starts with 2. Yes, 2 3. In the sense I have chosen 1 2, I have to take 2 3. So I have to write 1 3. And next, when I am going to take 2 3, I have to take 3 4. Again I have an element 2 4. When I am going to take 3 4, no element starts with 4 in R. So that is what R square is. In the sense, when I have taken 1 2 and 1 2, I'm sorry, this is wrong, right? I'm sorry. See here, I'll tell you once again. I have a relation R 1 comma 1, 1 comma 2, 2 comma 3, 3 comma 4. Again a relation 1 comma 1, 1 comma 2, 2 comma 3, 3 comma 4. Now let me write R composition R or else R square as, first I have taken 1 comma 1 from this first relation. Again the same relation I am writing. Either I have to take 1 1 or I have to take 1 2. Why? Because continuation element should be there. If you are going to take this element, you will get 1 comma 1 in R square. If you are going to take this element, you will get 1 comma 2 in R square. Right? Now let me take 1 2. Fine. I have to choose 2 3. Why? Because continuation should be there. But here I have not taken 2 1. 2 element is not taken. So 1 2 2 3. I have to write 1 3 in R square. Just you can observe here itself. Suppose let me take xy, yz. So if xy yz is there, I have to write xz in R square. So remember, in R square, if x comma y is in R, 1 2 is in R, and yz in R, implies xz should be in R square. I have clearly told you this in the previous module also. You just go through it once. So I have chosen, coming to the proof, I have chosen R as transitive. I have to prove that R square is subset of R. Fine. Now let me prove. Now I have proved, just by the definition of R square, let me take there exists an element y in a given set. Then xy belongs to R, yz belongs to R. Why? Because I have taken one element. Then this ordered pair should exist in R. If this is the case, what I have assumed is, since I have assumed R is transitive. So as per the definition of transitivity, if xy, yz is there, xz should be there. So xz belongs to R, right? And hence I can write R square is subset of R. Why? Because in R square xz is there. In R xy and xz is there. I'm sorry, yz is there. So it is a part of R square. So clearly R square is subset of R. Now let me prove the converse part. Suppose R square is subset of R. I have to prove R is transitive. R is transitive. Let me consider two ordered pairs xy and yz belongs to R. Implies that if xy and yz is R, then xz should be in R square. So I can write xz should be in R square as per the definition of R square. See here, I have done this. xy in R, yz in R implies xz should be in R square. So xy, yz in R, xz should be in R square. So from these two conditions, I can say xz is also, if xz is in R square, since R square is subset of R, I can write xz is also in R. Now from this condition and this condition, xy, yz in R, xz in R, it follows that R is transitive. I'll repeat it once again. First I have chosen R is transitive. I'm going to prove R square is subset of R. Fine. Now R is transitive. So in R square, I have already told you, this is just a key point to remember. In R square, if xy is in R, yz in R, then xz will be in R square. Now what I have taken is, I have taken two elements xy and yz in a given relation R. Now I have already assumed that R is transitive. So as per transitive definition, applying for these two ordered pairs, I'll get xz in R. So clearly in R square we have an element xz. Right? Just now I have proved in R square I have an element xz. In R also I have an element xz. So from this condition 1 and this condition 2, clearly I can say R square is subset of R. Now coming to the converse part, I have assumed R square is subset of R. Now I am going to prove R is transitive. Let me take two ordered pairs which belongs to R. Now since I have proved just now, if xy is in R, yz in R, then xz should be in R square. From equation 2, I can write xz belongs to R square. If xz belongs to R square, since R square is subset of R, xz should be in R. I have done in equation 1, xz in R. This implies, look at these two conditions, xy and yz is in R, then xz should be in R. So from these two conditions, I can say R is transitive. Hope it is clear. Thank you. Continue in the next session.